Okay, going to work through another simple harmonic motion question. It's very similar to the last one we did. I just sort of switched up what I gave you and what I asked for. I'm going to doodle a little picture to help us get this in our brains. We've got a spring. It's always going to be horizontal. I won't give you any vertical. If I do, I'd make it really obvious that it's vertical because then gravity becomes a factor. So we've got this horizontal spring, a mass is attached to it. The mass is 250 grams, but I'm going to put that in kilograms. We'll need that for later. And it says it's wobbling back and forth in vibrational motion. Because it's a spring, it's simple harmonic motion. Goes shooting away to the right, stops for a split second, and then comes back to what we call the equilibrium. Then from there, it goes away to the left to the amplitude, stops for a split second, and then back and forth. So kind of going back and forth like that. I got the 250 grams. Students, notice that the time period is 0.5 seconds. I can't do anything with that right away. Well, I'm going to use that, but let's jot that down and keep reading our numbers. So there's the 0.5, and the maximum speed is 1.5. So when it's at the equilibrium, it's going 1.5 meters per second. And then from that, there's enough with just that little bit that we can figure out the spring constant, then the amplitude, then the velocity, and then the position. The weird thing about the simple harmonic motion stuff is kind of working through and picking the right equation. This one is a little bit trickier than the last one we did. Well, it kind of looks trickier to me, but if you go back and look at the equations, there's enough there that we can use the time period to start. In the time period equation, there's just the three things: the time period, the mass, and the spring constant. So if I tell you any of the two, you can solve for the third. In this particular case, we know the time period, 0.5. 2 pi is just going to hang around for a little bit. We know the mass, the 0.25, and then that's divided by k. There's enough there that we can solve for k. It's a little bit of an algebra thing. If I take the 0.5 and divide by 2 pi, and then if we square all that, then I'm left with 0.25 over k because I've got rid of the square root. And the 0.5 divided by 2 pi, and then all squared. That turns into this ugly decimal. I'll just put down a few of them. Oops. 0.0063. And it keeps going, but that's enough for me to write down. To solve for k, I multiply both sides by k, then divide both sides by the 0.0063 number. Basically, the k and the 0.0063 number trade spots. When we crank that out within rounding, I got k to be almost 40, 39.5. So from the time period equation, we can get the k. Once you've got that, I think it kind of falls apart. Obviously, I'm going to keep working it through, and I'll show you a couple shortcuts. But once we have the k, then it's just a matter of working through the equations. The second part of this one, I zoomed to get it out of sight, but I asked for the amplitude. Our amplitude is connected to the maximum speed. From conservation of energy, we've got this equation. We now know the k, so we can just plug that k in. We know k, we know m, we know the maximum speed. We can use all that to solve for a. That's a perfectly great way to do it. The maximum speed I made up was 1.5. The k that we just got the math on is 39.5 with some rounding. The mass was 0.25, and then we're multiplied by a on the end, so we can do some algebra to solve for a. So crank that way out. If you've started that way or did it that way, crank it out, see what you get. Another thing we could do is from that weird omega thing, omega was root k over m, which was equal to 2 pi over time period. So we can change our Vmax equation, and we can say Vmax equals 2 pi over time period multiplied by amplitude. Why I kind of like this way is we were given the time period in the question, so we don't have to use a rounded off number to solve for this one. We don't have to use the rounded 39.5. The maximum speed was given as 1.5. 2 pi is always 2 pi. The time period I made up in the question was 0.5. then we're multiplying by amplitude. A little bit of algebra. Amplitude all by itself is 1.5 times 0.5, and then all of that divided by 2 pi. When I crank that out, I get an amplitude of 0.12 meters within some rounding. You could call that 12 centimeters. You don't have to go to centimeters, but that's what it is. If you did it the way that I first started off, the root k over m times a method, you should get the same number within rounding. They should match up at the end. Back to my question. Number 3 was, what is the velocity after 1.3 seconds? There's only one way to do this one. When you're asked for a position or a velocity at a specific time, you have to use what I call the tricky trig equations. So I'm going to scroll down. Part 3 asks for the speed at a specific time. We have to use tricky trig. Works out to be that. Oops, I wrote it with the delta t, so it looks like that. In this one, we know the maximum speed. We have to use that omega thing again. There's 2 equations for omega. From what I said before, I think it makes sense to use the 2 pi over t version. So really we say that the speed is the negative of the maximum speed multiplied by the sine of, in this case, 2 pi over the time period was 0.5. Sorry, a little bit messy. And then multiply all of that by the time you're curious about, which if you scroll back up, I was curious about 1.3 seconds. I call this a tricky trig one because you have to remember to be in radians. This is the only time in the whole course you have to be in radians. These 2 equations, the x with the cosine in it equation, and then this v with the sine in it. Now it just turns into number crunching. This equation, the rounding can blow up really huge, so it depends how you round off the pi, depends how you round off, you're dividing and multiplying. I carried a lot of digits and I got positive 0.88 meters per second. If you disagree with the number, don't freak out. I don't get too worried about your actual answer to this, as long as I see that you knew what equation to use and how to get it. The 4th question in this example is the position at a specific speed. Position at a specific speed, there's 2 ways to do it. We could go through the tricky trig equations twice, do it once to get the time, and then use the time to figure out that exact position, or we could go back to just conservation of energy. When the mass is whipping through the equilibrium, all the joules are kinetic energy. So I know that the 1/2 mv squared at the equilibrium gets shared between both kinds of energy at other positions. And the example that I worked through before this, I gave you the amplitude. So in the conservation of energy question, instead of saying 1/2 mv max squared, I said 1/2 k a squared because we knew the amplitude. In this particular question, we now know the amplitude. We figured that out earlier. So we could say equals 1/2 k a squared, but that a might have some rounding in it. You wouldn't be wrong, just watch your number, your rounding. Either way, I'm going to do it with the 1/2 mv squared. I can cancel out all these halves. I'm not going to worry about this one, I'm doing it the other way. From the beginning, we knew our mass was 0.25 when we put it in kilograms. Sorry, that's a little messy, let's try again. So we knew the mass was 0.25 in kilograms. The maximum speed was given as 1.5. Again, mass was 0.25. We're curious about where it is when its speed is dropped to 0.5. The k, I'm not going to do another version. I'm just going to put in my rounded value for k. I don't think it's worth doing any 2 pi over t to try and get rid of, to avoid the k. And then I'm solving for s squared. It's a little bit of algebra. It cleans up a little bit. The 14.1 s squared, when you square the 1.5s and the 0.5s and bring them together and deal with the 0.25, I got it was a nice clean 0.5. And then flip-flopping things around, s works out to be, and square rooting, I got 188 in meters. That kind of makes sense. If I convert it to centimeters, it's just inside the amplitude. So since it's going kind of slow, it's not very far from the amplitude. So this one, same basic idea as the last one. Just work through what you're given, find the right equation to match it, think about your conceptual things. If you're asked for speed or position at a specific time, you have to use one of those tricky trig. If you're asked for speed or position at another speed or position, then you use conservation of energy.